Alright, so I wanted to create some videos for Class 9. I'm going to try to catch up. Unfortunately, didn't realize I hadn't recorded any yet. So we're introducing Chapter 4 from Shigley, which is the beginning of deflection and deflection. So today's topic is superposition, but first I wanted to start out with talking about spring rates and thinking of structural pieces as being springs. Talk about axial and torsional deflection and beam bending deflection. Right? These are maybe the three that we're most concerned of, and then using superposition to find deflections by a combination of different loadings. So there's a number of things that I didn't cover in class, and I'm going to break this down into various smaller videos, so they're digestible pieces. Okay, so this is stuff that I did talk about in class right here, are spring rates. I didn't really think of structural pieces as being similar to springs. And I had a couple springs over here to as just visual things. Well, where force creates a deflection, and if it's a linear spring, it will have a straight line relationship, and I like to have del instead of y most of the time when I write this right here, because we know that force is equal to a spring stiffness times the displacement, right? So this spring right here has some k, and is most likely going to be linear, at least through a certain range. And that k, that spring stiff, is really the slope of this curve. All right, so this is a linear one, but there's nothing that says that a spring necessarily has to be linear or that a piece has to be linear. And so one instance might be where the slope is actually increasing as we come through, and we call this, say that this is a stiffening spring, right? So it's getting, the slope of it is getting steeper as you come along. We can also have one where it actually starts to get softer, and they're showing this in this example. It's got a kind of an arch to it through there. We can also have one where there's a sudden change to it as well. And these are non-linear behaviors. But what you're seeing here is now this is getting less and less right here. So we're saying that up to that point, as it was getting over there, we're softening. Right. So these are non-linear right here. And they make problems more difficult. So we would prefer to stay in the linear range of things because they're a lot easier to deal with. A good example to start on, to hang our hat on when we're looking at stiffness and looking at deflection, is to think of the simplest case. And that might be, we'll have some piece right here, and it's fixed at one end with a force right here. We know what the cross-sectional area is, and when we apply a force, it gets longer by some amount del, and it originally has an original length of this, but it gets longer. I think this is a pool noodle is an excellent example piece to use, right? That we could pull on this, so we could feel that we're stretching on it, so that that causes a strain equal to del over L. But we also know that force causes a stress of F over A, and that these two things are related to each other by Hooke's law. Right? So we can replace these into this and say that F over A is going to be equal to E times del over L. Right? That's Young's modulus right there. So we could solve for del. Right? This is the deflection that we care about, and it's going to be AE. No, excuse me. Got it backwards. Sorry. FL over AE. Right? So there's our simplest scenario for deflection. And if we want to compare it to a spring, we could just remember that a spring rate could be defined as F over del, right? That's a K. So we could just take these two right there, and we find that this is AE over L. And I've done this in a previous class because it's a good, like, simple scenario to kind of keep in mind and use as a foundation for you know, trying to remember these concepts for a spring rate. And a similar one would be for torsional deflection, right? So we have like a little piece, and once again, the pool noodle is a good example where we do a twist on this, and sometimes these just rub off the dry erasers here, but you know, we can kind of try to do this same thing right there. Right, so I've drawn a line on this, so maybe you can see that. I don't know. You can see my line. Oh, come on, there you go. And if I twist this, I got to put the load right there on the end, so you can see that it's going to remain a straight line. Although it doesn't, maybe it doesn't look like that on that, but it is a straight line. Or at least we interpret it to be. So if we had a straight line that we were to draw onto this, and then a line like right there, and we were to apply a torque, right, it would shift like that right there, right, and it would turn like this amount right there. So it's hard to draw that in there. Maybe it's going to have a theta. We call that a theta amount of deflection. And this thing is going to be like L long, so it's going to be fixed here at the end. We would find that the deflection in this is TL over JG, right? Kind of a similar setup right here, where there's the load, here's the length, here's a cross-sectional property, and here's a material property right there. So you can kind of think of it in those terms. And then we could also arrange, if we wanted to, a quasi-stiffness here, right now. So this is sort of like a rotational stiffness. That's why I put a theta in there. So we put load over deflection, and what we end up finding, we have JG over L. So sort of in a similar way that we have stiffness up here, we have cross-sectional property, material property, and overall length of this piece right here. Now this would probably have like Newton meters per radian, right? So Newton meters per radian or something along those lines in terms of its units, whereas this would just be like newtons per meter, or it would be pounds per inch, that type of thing. Now, once again, I didn't make this into an animation, and I kind of wanted to, but I went through this kind of quickly in class. I don't really want to spend a lot of time, but it is good to remember where this very important equation, this guy right here, call this the Flexural Equation, or Euler's equation right here. And this really is a very foundational equation in mechanics of materials to decide how moment is related to the bending, right? And it starts out with the geometry. What we do is we take a little slice of this thing with a radius of curvature of rho, and then we set up a coordinate axis where y is coming up, is going upwards through the neutral axis. And then we pick a location, an arbitrary location. In this case, it's like right here, and we know, like through the down the center of the line right here, we're going to say that that's going to be equal to like the original length, like the original section of this right here. But like a little bit higher, this would have been the same length as this right here, but now it's been compressed, right? So because we've made a curvature to the thing, right? So if we were to, I don't know if this will show up either, but if we were to, let's just take a section of this right here, and we'll draw a straight line right here, a straight line there, and a straight line there. Okay, so I've drawn these three lines, And as I come up like this right here, and I don't think I can prove this to you, but the top one gets shorter, the middle one stays the same, and the bottom one gets longer. Right? So we have compressive strain on the top and tensile strain on the bottom of the three lines, and the one in the middle is going to remain the same original length. Well, if we want to figure out what the strain is of the top part right there, we take the length, the prime one, and subtract out what the original length of it was. Right? That's the original length. And divide it by the original length. That's just the definition of strain, right? So it has gotten shorter, right, along that length right there. We can also, if we wanted to find this length right here, the length of this thing, we would take this delta theta and multiply it by p minus y right there. Right? And if we want to find this length right here, we take, I said p, I meant rho minus y, right? So that's just going to be the distance up through there. If we want to find the original length, it's just going to be rho times delta theta. So what we can find right there is that we're just left with negative y over rho. You can see how the logic of that works out. All right, so this is just a geometry statement. It's true because these lengths have to be the same, right? I mean, this length right there, yes, that is the truth, and this minus that has to be the amount it's gotten shorter. Notably, it is negative from where we're shown, which means there was compression from, at least from that direction that we were going. And we could see how these cancel out right here, how that is going to cancel out with this part right there, right? That and that combined. So we just have y over rho here, you know, and also those theta is going to cancel out on top. All right, and now we have Hooke's law, right? So this was just a geometry thing. This is just a material property that we know. We know that stress and strain are related to each other, at least in below yield, right? As in a linear way. We also can say that if we wanted to find the stress, and you know, we're going up in the positive y direction right here, we know it's going to be compressive. So we can say that it's going to be my over I, right? And that I is about the axis that's coming, you know, through the into the page. So with these three statements right here, right there, thrown into there, and this thrown into there, we have this statement, which so far nothing new. Now we also want to know about deflection right here. So this is, so far we haven't dealt with anything that's deflection. Now this particular source of this decided to call this V for some reason. We could just as easily call it Y, maybe to separate it from this. But and so like Y is a position, whereas this could be a deflection, right? That's you're separating it out, but I kind of prefer to keep it as Y. So they're showing like this little cantilevered scenario right here, and what we're really trying to say is like, so here is like, for a small little segment of this piece, we could figure out what the deflection is here compared to there, right? So this is what we're saying. We have V plus dV, small increments, over a smaller spot. So first off, what we're saying is that the arc length of this thing is approximately equal to dx. If we're talking about small stuff, that we okay, this is the length of the arc versus this is the distance, and the arc length is going to be rho times d theta onto it. So we can also find that the deflection that's going to be here is can be easily be said as dV is equal to this the angle that's in here, theta, not d theta, but this angle theta of the thing. let's see if I'm saying this all right, times dx, right? So like all we're really saying is here's dx, here's theta, and here is dv, right? Or you know, that's basically all we're going to say. It's really just the slope of the same thing. So this is really just sort of, you know, understood as part of the thing. So because of that, let's see if I'm going to say this the right way. We have yeah. 1 second. Let me pause for a second. Let me catch my breath. Okay, I just want to organize my thoughts here. Okay, so two separate things. This guy and this guy. This is coming from the fact that this arc length is, for very small angles, is going to be equal to this incremental distance in the x direction. This one right here is really coming, I think, best described by the slope, right? So here's theta times dx gets me this displacement, but I also know that theta, at least the d theta, has a relationship to dx, right? And so this guy right here, he's just repetition of the slope part right here. So when we rearrange this guy like this, right? So all we did was say 1 over this is equal to d theta dx. Simple statement. Therefore, the derivative of theta with respect to x is equal to this. But it's also equal, right? So also right over here, dv dx is equal to theta right here, right? So let's take the derivative of this right here. And if we do that, we end up with the second derivative of displacement. And so that, in a very clumsy explanation, is the derivation of the Flexural Equation. And where do we use this? What is it used for? Well, it's good to put this together. I really think this is an excellent summary, a thing to like maybe memorize, to look at closely, to try to like associate many of the or the main topics of mechanics of materials, especially when it comes to stresses and deflections. Because already here at the top, we have 3 diagrams that we've been regularly using, right? The free body diagram, that's going to give us the reaction forces, right? So that's FBD, really important. We have the shear diagram, which we know is integrating the forces up here, right? So it makes a lot more sense when you see one of, like an example figure here, or maybe we had a continuous function up here, but we are integrating a step function, if you will, where we're coming through here. This is a step, and then this is a step, and then this is a step right here. So the integration of that just becomes this step itself right here. And then we integrate this, and we got our moment diagram. We've been doing that all along to get stresses. Well, we can also integrate this. Okay, so when we get to this moment diagram, we can inject the Flexural Equation. Right, that is still the moment as a function of position as we're going from left to right, and we could say that it equals this. So now, if we wanted to go backwards up here, we say, well, actually, if we integrated to go downwards, we're differentiating to go upwards. So we take the derivative of this is actually the shear diagram. The derivative of that is actually the load. And then if we want to go downwards, we have to integrate again, just because we were integrating as we were going down. And so if we integrate the moment diagram right here, we end up getting this right here. This ends up being the slope, right? So we're solving for this. Of course, we have to divide out by EI at this point in order to answer that. So here we go. That's them showing that these what these magnitudes are, so we can get the slopes at the end. And then if we also, once again, integrate this, we're able to get what the deflection is. and it's going to be 0 at the ends, and here we're going to have a maximum. So we're going to continue in the next video, but this has already been done for you. Right? This method of finding deflections for various common scenarios, and a very important book that covers a lot of this is Rourke and Young's Formulas for Stress and Strain, or now it's just called Rourke's Formulas for Stress and Strain. And these are excerpts that the Shigley has inside them, right? So here's for a simple force on a cantilevered beam. And you can see here's the shear diagram and the moment diagram for this. So my keyboard over here. We also have, here's one where it's just a force at arbitrary location. There's a shear diagram and a moment diagram for how this is taking place. And here is the maximum deflection at the end, right there. But there's also the deflection anywhere along between B and C, and here's the deflection anywhere between A and B. Right, I'm not going to cover all of these, but some good ones to recognize. Here's one that I will walk through in the next video, I believe in the next video, because it's a simple one, but here's what the result that we can be expected to look for. And here's what the shear diagram looks like in the moment diagram for there. Here's the last one I'll mention, because this is probably one of the most important ones for simply supported beams, because it's with this, and we'll describe the use of superposition. We can do a whole lot of things when there's multiple forces and stuff going on there. So we'll use this when dealing with three-dimensional shafts. There's also another one that we might want to consider. Let me think. Yeah, this guy right here, perhaps. Right. So if we have an overhung shaft, simply supported shaft, here's one also that we might consider wanting to use. So anyway, that's at the end of the video here. Trying to get you, some of these things are a review of mechanics and materials. Hopefully you have covered this in a little bit. If not, it's at least a familiarization tour. So I'll make another video. Hopefully it won't be too long.